Hello, everybody, and welcome to today's MacDermid Enthone session on the best practices for Passivate control. My name is Robert Collin. I'm the America's Technical Manager, and I'll be the moderator for this event today. The presenter is Michael McCoy. He is our Anti-Corrosion Business Development and Product Manager. Please submit the questions as you have them, and we will answer them at the end of this session. If for some reason we can't get to your question specifically, we will follow up with you via email. And again, thank you all again for participating to be reacquainted on the best practices for Passivate control. And with that, Michael, the session is yours.
Good morning, everyone. Mike McCoy, MacDermid Enthone, Business Development, Product Line Manager for Anti-Corrosion Products. Anti-corrosion has been my field of expertise for my entire career, for about 20, 25 years or so. We're going to go through the steps for proper passivation control, different items that are necessary, and different items that are contaminations. And I wanted to just start by first giving a little bit of a historical perception on where we are today with trivalent passivates. You know, back in 1990 or so, I remember traveling to Europe, and I kept getting the question, when are you going to have a trivalent yellow chromate? And I said, well, that's never going to happen. And now looking back at it, if you look at the historical anti-corrosion time frame, back in the 60s and 80s, we used cyanide-based electroplating solutions and hexavalent chromates, two of the easiest solutions to operate, user-friendly, wide operating windows, not a lot of control parameters needed to put in place. You can see corrosion requirements were also significantly lower, 250 hours or so. In the 1990s, we started coming up with cyanide-free zinc plating solutions, and they had some of their own hiccups in the beginning, such as delayed blistering. But we also started to put on final finishes like silicated sealants for extra corrosion resistance. You get to about 500 hours or so. In the later 1990s and 2000s, zinc alloys became popular. Extra corrosion resistance. We started to use trivalent clear passivate solutions. So we were starting to move out of the hexavalent area. And we still were using sealants, but the requirement was about 1,000 hours. Well, since then, and since the elimination of hexavalent chromate by REACH regulations, we've really increased our technology and our capabilities to increase the performance of our final finish. Protecting the part is what we're trying to do. And in the time frame, and because REACH regulations and other regulatory requirements, it's forced our industry to become better, provide better technology. And what that better technology really has done for us as well is also put a microscope on how to operate these systems as far as control and contamination levels, and also bath lives. And that's something we'll be talking about this morning as well. So you can see here a little quick example about some of those corrosion resistance. First, we're looking at, the zinc with hexavalent chromate. You look at heat treatment, salt spray after heat treatment, and you can see that the trivalent and zinc before and after is about the same. And then when you start getting into the hexavalent chromates, whether it's zinc iron or zinc nickel, the red bar is after thermal shock. And you can see a significant difference in the performance as it's related to heat treating. Now, whether that's baking for hydrogen embrittlement or whether that's service life, under hood applications, trivalent passivates are going to perform better than hexavalent chromates in heat applications. So what are we talking about here, right? We're talking about an immersion process. We're talking about a conversion coating. We're talking about whether it's zinc alloy, converting the very, very thin area between the film or between the deposit and the environment that it is in. That trivalent acidic environment, and we are converting that zinc or zinc alloy to a zinc chrome complexed gelatinous water-based film. So as mentioned before, the hexavalent chromates were based on sodium dichromate, chromic acid. Trivalents are based on chromium nitrate, chromium sulfate, those types of compounds. And there really does need to be a distinction. The automotive industry really wanted to put this forth in our minds when hexavalent chromates were being eliminated, that there is no such thing as a trivalent chromate. By definition, passivates are trivalent, chromates are hexavalent. So terminology can be very important here. And I had a conversation on Friday with a customer still calling them trivalent chromates, but that's okay. It's just a distinction that needs to be made. So why do we put them on? We want to increase corrosion resistance. We want to improve the appearance. You take a zinc part and you don't passivate it or chromate it in some fashion, it's going to corrode very, very quickly, and it's going to turn dark. So we want to have a good appearance, whether it's a blue bright finish for, say, a drawer slide, or whether it's a dark black finish for, say, a fuel rail or a hydraulic fluid carrying tube. The appearance is very important. Some also improve organic coatings, and some are just for identification. Clear is left, black is right, one of those types of things, or even the green dyes for electrical grounding applications as well. So how do we do this? We have a solution here with a pH, you can notice on the left-hand side and the right-hand side, of about 2. That's about an average pH for passivates. So when a part is immersed into the acidic environment, you can see that the pH rises to about 5 or so. And when the pH rises, the zinc is dissolved into solution as a contaminant. That's what's happening during this process. Chrome is being deposited at that pH rise, and zinc is being dissolved. And you can see the color appearance on this brake caliper just happens to be blue. So what we're left with after the process is, on average, the most popular trivalent iridescent passivate films are going to be about 250 to 350 nanometers. So they're very, very, very thin. They're also, like I said, gelatinous. They can be scratched. They need to be cured for 24 hours. They need to be dried properly. So care must be taken in the formation of this passivate, as well as bulk processing after the passivate has been formed. It scratches very, very easily. And another large distinction between hexavalent chromates and trivalent passivates are the self-healing characteristics. Hexavalent chromate gets scratched, the chrome is kind of going to self-heal itself and still provide some protection. Trivalent passivates do not have that capability, which is another reason why in the 90s and 2000s we started to implement sealants on top of chromates and passivates. We can get all sorts of different colors. You can see in the upper right-hand corner, that's what would be more typical of a thick film iridescent passivate. On drawings, it's called clears. Some drawings, some older drawings might say colorless, but it is going to have some iridescent pinkish green hue to it. On the left-hand side, you can see a blue bright. That's the stuff you find really at the lowest corrosion resistance, highest appearance. It's on your fasteners you buy at Walmart and Home Depot. And then on the bottom, we have blacks, and then just a really more of a standard clear. For that reason, we have a wide variety of passivates. We have this list here contains cobalt, which is on the SVHC list as a potential for elimination and replacement. And you can see that we have zinc passivates, zinc nickel, tin zinc, zinc iron, blue, thick film, black, different levels of corrosion resistance, different appearances, different performances. So choosing a Passivate can be very important in knowing what you want at the end result. What is going to happen to this part in service life? Is it going to sit on a wall and be a fastener for a picture frame, or is it going to be an underhood application? So we have cobalt-containing Passivates, and then we have cobalt-free Passivates if REACH regulation gets there and eliminates cobalt metal. Again, multiple different processes for multiple alloys and heat resistances and corrosion resistance. So I was talking before about the film thickness, and you can see that a hexavalent blue chromate is about 25 to 80 nanometers. Chrome content in milligrams per square meter is on the lower side, as is just chrome metal. Trivalent blue chromates, your decorative blue type of, Passivates, are going to be similar in thickness and in chrome content. When we really start building a much thicker film, now we're starting to get into higher corrosion resistance. So the iridescence trivalent Passivates, 200 to 400 nanometers as mentioned. And then the older school yellow hexavalent iridescent are going to be similar in film thickness, but obviously they're going to have much more chrome in them. And if you look at that first slide that I had, we're trying to eliminate hexavalent chrome out of the systems because they wind up in landfills at some point. And then black coatings, you can also put olive drab on there as well. You're really starting to generate some serious film thickness on a hexavalent black, almost up to 1,000 nanometers. And then because the film thickness is greater, obviously the total chromium content is going to be greater as well. This does not necessarily mean it's going to be more corrosion resistant, however. So when I start talking about parameters, and I want to just mention that one of the good things about chromates and Passivates is that they are adaptable. Okay, so the information that I'm going to be providing to you is dependent on what you're doing in-house, predominantly on the plating line, what solutions you're using. Acid versus alkaline could have completely different operating conditions for the same product. That's because the grain structure is different. An alkaline deposit wants to absorb in a Passivate. An acid deposit is more laminar, and you have to really bite through it in order to get that chrome precipitation. So the substrate is completely dependent on operating, or I'm sorry, the operating conditions can be dependent on the substrate as well. So what does all this mean? It means you take your information, you do best practices, and then you adjust to the system that you're doing it with. Barrel and rack, huge differences in operating parameters, potentially, depending on your plating line. So all this information is meant for you to take back, to think about, and then to adjust any conditions that are adjustable. Not everything can be adjusted. And we'll get into some of those parameters later. Most important parameter is pH. pH, as we showed in that second slide, rises as you form that Passivate film. So it has to be controlled. Standard between 1 and 3. So your black and your olive drab chromates are usually around 1, maybe a little bit lower. And your trivalent Passivates can be as high as 2.8 or so. So what does that mean? When we were talking about the pH in that diagram before, the lower the pH, the more zinc you're going to dissolve off the part, the faster the film is going to be formed. Not all films should be formed quickly. That's another differentiator between the different Passivates themselves. Some require 30 seconds of immersion. I used to have a hexavalent chromate that was 15 seconds and no one could control it because it was too fast. pHs that are higher is going to form that film slower. Sometimes you want that. Depends on what you're trying to do with the Passivate itself. So controlling the pH, pH papers will work as long as you can still see the color change. The trivalent Passivates are usually darker in color, so pH meters are important. Automatic control on your plating or on your Passivate solution is highly recommended. The pH probes need to be cleaned on a regular basis. You really, really need to monitor that in the range of about 0.2. So if your standard operating pH is 2.3, your window would be 2.1 to 2.5. And you'll notice a difference in performance and appearance at 2.1 as well as 2.5. So as I was talking about the pH on the left-hand side, you see the weight of the deposit. You could also call that the film thickness. So the lower the pH, the more zinc you're going to be dissolving, the faster you're going to be forming that film. Then you're going to reach your optimum level. And that's where you're going to get a good color change depending on what Passivate you're using. And then if the pH gets too high, you don't remove enough zinc. And actually, if it got too high after that, you wouldn't even be able to precipitate the chrome out of solution. Similarly with the zinc dissolution, and zinc dissolution we will get to in a little while, because that is extremely important with trivalent Passivates. So you can see that the lower the pH, you're going to be under passivated. The higher pH, you're going to be over passivated, and you're also going to dissolve less zinc at the higher pH. So if you're able to run a process at a higher zinc level, it is certainly recommended, because you're going to dissolve less zinc, which is a contaminant. Concentration. Yes, concentration is important. I'm not saying it's not, but the majority of the decrease in concentration is related to drag out, particularly in barrel operations. The blue Passivates that make up that 3%, 5%, 10% at the top are obviously going to be more affected, because when you drag out some of that solution, the difference in concentration due to drag out can be significant at a lower concentration of 3 to 5%, say, versus a higher concentration as high as 15 to 20%. It is going to have an impact, but it's not going to be as detrimental. And they can be analyzed by chromium content. So you can titrate for it. You can use AA, you can use ICP, and then get a relative concentration based on that. You can do that on the benchtop. Similar concentration changes, lower concentration versus higher concentration. So the higher concentrations are going to produce a thicker film. Lower concentrations are going to be a thinner film, and you're not going to have the color change, and you're not going to have the chrome precipitation reaction that you're looking for. Agitation. Can't stress agitation enough. Some Passivates, including black Passivates, agitation is extremely critical. But the most important thing about agitation is that it's uniform, particularly in rack operations. You need that reaction to take place uniformly across the entire rack envelope. So what's happening is with the agitation is the precipitation in that very, very thin interface between the zinc and the acidic Passivate solution, that interface needs to be changed over very, very quickly, because once that chrome precipitates, you want to get more chrome in that area again so you can keep building that film. If you don't change over that interface layer, you will not have a good Passivate film. You won't have the proper color, and you certainly won't have the corrosion resistance that you're looking for. So when I mention type of application, plating line, and part geometry, you know, if you're doing brake calipers, you can have the most aggressive air agitation you want because those things aren't moving. However, there's a tremendous a lot of applicators that run stampings on gravity hooks. If you have a high volume of air agitation, you're going to knock those parts all over and knock them off the rack, and they're going to wind up in the bottom of the tank. So one type of agitation does not fit everybody. So we talk about solution movement with eductors is extremely common, especially in Europe. Vigorous air we mentioned, even cathode movement. And I've seen combinations of all of these being performed. Usually it's 2, not 3, but you could have cathode movement and eductors in one Passivate tank. It's very common. Barrel, not so much. You could have continuous rotation. You could have rotation that just kind of turns maybe a quarter turn every 15 seconds. But because it's the gelatinous water-based film, you're going to get some scratching, especially on black Passivates because they're thicker. The Passivate film is going to scratch. So best practices is to do offline basket passivation from barrel plating operations. That will produce the best color and that will produce the best corrosion resistance. Can't stress that enough. Extremely important. Why go through all these efforts to produce a substandard part that looks bad and doesn't perform the way you think it would? Do it offline. That's the way to do it. This is a very interesting slide, and I actually have a pretty good story about something like this. If you look at the bottom, besides the holes coming up, which is not proper, the smallest and the lowest amount of air agitation is in the bottom of the tank near the air pipes. And then as those bubbles come up through the solution, they get bigger and combine with other bubbles, and then you notice that they're big, huge blooms that come out. So I had an applicator that had a longer, it was a 500-gallon tank, but it was longer and flatter. It wasn't that tall. I mean, it was probably only 4 feet tall. And we had to, it was an automatic line. We actually, in a 90-second immersion time, we had the parts go down for 45 seconds, then go back up, and then back down for another 45 seconds. And the reason for that was to get the bottom part of the rack through the upper part of the solution so we had more aggressive air agitation. And before we started doing that, the bottom part of the rack looked completely different than the top part of the rack. We did the up and down every 45 seconds, and we got a uniform looking appearance across the entire rack envelope. So just because we had good air agitation, and the customer kept telling me that, how do you get more air? This is the best air agitation I've ever seen. I said, let's move it up and down and try to see if we can, and that worked. So air agitation is that important. And you can see that that goes directly towards film thickness. You know, yellow chromate solution difference in coating weight is approximately double under the same solution parameters and immersion time, simply because you're changing over that interface between the part itself and the Passivate solution that it's immersed in. Immersion time. Again, what type of Passivate solution are you doing? What application, rack or barrel? What type of plating line? You know, automatic plating lines, the old school return type Psychomaster plating lines, great lines, produce a lot of parts, but boy, can they be difficult on immersion times, because you could have something that's 10 feet deep and the bottom part of that rack is going to be in there twice as long as the top part of that rack. And then you have to take into account transfer time. It slowly comes out of the tank, it slowly moves over to the rinse tank, and slowly goes into the rinse tank. That transfer time needs to be taken into account of your total immersion time, because That part hasn't been washed off yet. You've still got chrome on that surface, and that reaction is still taking place. The one thing that's interesting and good about the three things I've talked about: concentration, time, temperature, concentration can go to pH, is that you can play one against another. If you have a time where you're locked into 40 seconds, but you need to develop a thick film that would normally take 60, 75, 90 seconds, you can lower the pH. You can change the concentration. You can increase the temperature. So you can play these parameters off of one another to fit the line and the application that you are dealing with. So although these are rules and need to be followed and are somewhat rigid, they are adaptable and can be played one against another. Similar graph with time. Longer time, higher concentration, over passivation. Short times, you're not going to have enough time to build that film thickness. Temperature I just mentioned. The temperature is related to the film thickness. It does play a role in developing that film. If you try to passivate something at 65 degrees, 70 degrees, it might not take at all. Zinc nickel is a very good example of that. Zinc nickel is a very hard deposit. It needs that extra temperature to help bite through the deposit. So the idea is to find your proper temperature for your situation and keep it there. That can be difficult. Might not sound like it's difficult, but if you have a Passivate solution and you're in Wisconsin in January and your rinse water is 50 degrees and you've just gone through a triple counterflow rinse and the parts have been in this 50-degree water for 5, 10, 15 minutes, and you hit a Passivate solution that's 120, 150 degrees, that temperature is going to drop immediately. It's going to act like a heat sink. So yeah, it needs to be maintained. It can be maintained, but things like the environmental situations like cold rinse waters need to be monitored as well. So the thicker, higher film iridescent Passivates are usually heated to higher temperatures, while blue Passivates are not. You want to take the chill off of them in the winter times and when you're making up new solutions. Another thing about temperature, you can see this is the first graph that we've had that has almost of a downward turn to it. And that is because as you are generating these Passivate films, what was I talking about in the beginning? Or I was talking about the chrome zinc complex. Well, what happens when there's no more zinc left and all you've got is chrome? You're not going to be building a film anymore. In fact, you're going to be stripping away the film that you had just put on there. And that's going to be, that will lead to, well, with hexavalent chromates, that would lead to slough off. In this trivalent world, it leads to thinner film deposits and lower corrosion resistance. Contamination is a really big point, and it goes to a couple of different avenues. Back in hexavalent chromate days, I remember checking zinc concentration in a hexavalent chromate a couple times, but it wasn't often, and it certainly wasn't every day. When the parts started to look poor, you would cut the bath or make a new one or make an adjustment, maybe increase the time, something like that. With trivalent Passivates, the zinc contamination in the Passivate film goes directly to corrosion resistance. Okay, so yes, we use 10 grams per liter as a maximum. There are Passivates, depending on how they're built. These Passivates are built with different organic acids. They're built with different sources of chrome nitrate or chrome sulfate. Depending on how they're built will depend on your upper limit for zinc contamination before corrosion resistance. I use 10 grams per liter. At 5 grams per liter is when you should really start thinking about making a corrective action though. Whether it's a decant, whatever your corrective action would be. Iron is even more important. You can only see 100 milligrams per liter on that. Parts in the bottom of the tank. Boy, will that get some iron up there quickly because the zinc will strip away. Tubular goods have bare steel on the inside. Cast iron has porosity. Even using powdered metal. So iron is a big problem, and it can also change the appearance and make blue passivates and clear passivates look more yellow. Copper's a big no-no. Any copper in there and you have a dark film, no corrosion resistance. It's usually coming from copper bus bars or some other source of contamination. Copper is extremely poor for proper passivation. So what does this mean? We're putting a zinc or zinc alloy part in a tank or in a passivate. We're forming the passivate solution. We're dissolving off zinc. That zinc contamination starts to rise. And then we start to reach our action limit, as I had mentioned, and then our upper limit. And then unless you're doing a significant amount of barrel work, you might reach a steady state where you're dragging out as much of the zinc iron as you're bringing in. But in most cases, you're not, and you have to put in a new makeup. And does that have a cost impact? The cost impact between a trivalent passivate and a hexavalent chromate is significant. And that's just dollars in the tank. Then you start talking about waste treatment. So having this up and down movement is very costly. I mean, nobody wants to take a solution that's 20% by volume, maybe it's a 500-gallon tank, and cut it by 50 or 75% because of this contamination. But you have to do it. So what we've started to look at is ion exchange systems to remove the iron and zinc. Okay, so there are other metals in the Passivate solutions that are meant there on purpose. We want to make sure we don't take those out. We want to make sure we don't take the chrome out. Okay, so we try to reach a level that we're never going to need to make up a new bath makeup. And that's a nice sweet spot to be in. So one of the things that MacDermid Enthone has started to put forth is a very significant sustainable solutions program. And what we do with these sustainable solutions, you can see that, we try to recover waste streams. We try to reuse materials. We have solutions to pull copper and or nickel and or chrome out of rinse tanks for POP lines. It's a tremendous savings for folks. If you don't have to keep adding nickel sulfate or nickel chloride, and you can reclaim the nickel in a drag out, that's a savings right down to the bottom line for purchases of nickel metal. And that's a tremendous amount of reduced sludge in your waste stream. And that's a lower cost and a lower hazards towards the environment. There's certain discharge standards that you can be fined for, non-compliance, landfills, so that all works. So not having to dump these tanks means a guy doesn't have to get on the hazard suit and go into the bottom of that tank and clean out any sludge. That's not a fun job to do. And if you don't have to do it, then you don't have to put, it's a much more improved working environment for everybody involved. So these ion exchange units that we have available does go to producing less waste. You're not treating as much chemistry. Again, the environmental footprint that we are all leaving on this planet is significantly reduced. So using these types of systems for Passivate solutions, that it's trivalent chromium and nitric acid and other acids. I mean, it's an acidic solution and it's a hazardous chemical. There's no two ways about it. These types of systems go to best practices. And that's what we all try to keep up with is best practices. Make sure your contamination level is low. Make sure you have a preventative maintenance system in place to handle contaminants. Make sure your concentrations are where they need to be and not higher than they need to be. Make sure your agitation is sufficient enough so that you're forming the film, but you're not just dragging chrome into the rinse tank next to it and sending it to waste treatment. All these parameters and all these techniques play along together to produce what we call best practices and are all significantly recommended. So with that, I would like to thank you for your time. Thank you for participating, and I'd be happy to answer any specific questions that you may have.
Hey, Mike, thanks very much. It was a very informative session on best practices for passivation control. Lots of things we take for granted and or forget during our tenure with working with these solutions. There were no questions submitted. So if you would like any additional information or any of the processes you've seen, equipment, or anything else, please contact Michael McCoy directly at the email on your screen. With that, that concludes our session. I hope you all have a safe day. Stay safe in your normal work. And as always, we'll see you next time.
Thank you.